Hi guys, I hope you are doing well. Thank you all for your good response and constant support that is encouraging me to do more such videos. So we are continuing our lecture series on question answers of irrigation water management. In this way, we will cover the whole chapter. So let's start it. Then the next question is soil moisture characteristic curve is a graph between dash and dash. Soil water potential and soil water tension, or soil moisture content and soil water potential, or soil moisture content and soil water tension, or both B and C. The correct answer is both B and C. So the soil moisture characteristic curve is a graph between soil water content versus soil water tension or soil water potential. Okay, we have already discussed these two things are similar but in opposite direction. So one is always positive and another one is always negative. So this is all about your soil moisture characteristic curve. So coming to the next question, that is under a very high suction or tension range, soil moisture characteristic curve is dash dependent, whether it is soil texture dependent or soil structure dependent or pore space or ball density dependent. So the correct answer is soil texture dependent, because the question is about a very high suction or tension range. It means it is like hygroscopic water, that is 31 atmospheric pressure. We know hygroscopic water is held at a very high pressure, that is 31 atmospheric pressure. So at this suction or tension range, it is the texture which determine the moisture holding capacity, because we know that clay texture has more moisture holding capacity due to its high adsorption capacity. And this is the reason why the clay soil or clay texture has higher moisture content at a very high suction or tension range as compared to the sandy or light texture soil. But in case of very low suction or tension range, that is near to saturation, so at this stage the texture has not a definite role, because here the major role plays the soil structure. So here the soil structure is the correct answer if the question is about the low moisture or tension range, and if the question is about high suction or tension range, so then the correct answer is soil texture. Okay, and under saturation, because near saturation all the pore space means micropore, macropore, all pores are filled. So at this stage both clay soil and sandy soil have equal quantity of water. But when the water level or availability of water decreases and the force of attraction or the force of adsorption increases, at this stage the texture determines the moisture content. So it is simple. If it is about high suction or tension range, the correct answer is soil texture, and if it is low suction or tension range, then the correct answer is soil structure, and especially in case of compacted and uncompacted soil. So in case of here in case of soil texture, clay soil has more water content than the sandy soil. Okay, but in case of low suction range, that is near to saturation, if you see the structure, in case of structure, uncompacted soil content, uncompacted or uncompact soil contains more water than the compact soil. Okay, so I think it is clear now. Then coming to the next question, that is which instrument is commonly used for measurement of saturation capacity, that is the maximum water holding capacity. So the correct answer is Rhizoxy box. So this skin Rhizoxy box is nothing but a simple tool, or we can say simple can-like structure, and in this can at bottom holes are there, and when this can is filled with soil and this can is placed in a plate containing water, this plate containing water, when the can is placed, then the soil present inside the can will soak the water through these holes, and after a definite period of time like 24 to 48 hours, all means soil pores will be filled with this water, and at this stage the saturation is achieved. Okay, so after that the soil is collected from this can, and it is normally weighted, and in the method of gravimetric method the moisture content is determined. So the correct answer is Keene Rayzouksi box is used for measurement of saturation capacity or maximum water holding capacity. And we have already discussed about pycnometer. Pycnometer is used for measurement of particle density, and core sampler is used for measurement of bulk density. And the next one is pressure plate apparatus. Pressure plate apparatus is used for measurement of soil moisture constants like field capacity, permanent wilting point, hygroscopic coefficients under lab condition. And the piezometer is used for measurement of groundwater level. Okay, so this is all about. Then coming to the next question, that is infiltration rate of water in tropics is dash as compared to higher latitudes under comparable soil conditions. So here the soil condition is same, but here the atmosphere or climatic condition is different. One is tropics, another one is temperate. Okay, so we know in tropics the temperature is always high, and in temperate region the temperature is always low. Okay, so here the basic concept is about viscosity. Then what is viscosity? Viscosity is the frictional force between two layers in case of a liquid. Okay, so if viscosity is high, then between two layers of liquid, the frictional force is high. And it has been found that the viscosity is inversely proportional to the temperature. If temperature is high, then viscosity is low. So under tropical condition, where the temperature is high, the viscosity will be lower. Okay, when the viscosity will be lower, it means that the frictional force between two layers of water is lesser. As a result, water can easily penetrate the soil. So that is the reason why the infiltration rate is always higher in case of tropics as compared to temperate regions with the comparable soil conditions. Okay, so I think it is clear now. Then coming to the next question, that is according to Poiseuille's law, under saturated condition, the flow rate of water is directly proportional to that power of the radius of the pore. So remember one thing, this Poiseuille's law is applicable to the saturation water movement in soil. So it is applicable to saturated soil. It is applicable to saturated soil, and it indicates the water movement in a saturated soil, the flow rate of water in a saturated soil. So it always says that the flow rate, is always directly proportional to the fourth power of radius of the soil pores. Okay, sorry, this is the fourth power. Okay, so we know that soil contains different pores, micropore, macropore. Okay, so the radius of these pores varies according to soil, and this radius determines the flow rate in a saturated soil. So this is very important thing. Remember this thing, and this is according to Poiseuille's law. So according to Poiseuille's law, under saturated condition, so this kind of question be asked, Poiseuille's law is applicable to which soil? So it is for saturated soil, and it says that the flow rate is directly proportional to the fourth power of the radius. And applicability of this Poiseuille's law is, this is the reason why always saturated hydraulic conductivity, that is hydraulic conductivity under saturated soil condition, is always higher in case of sandy soil, because we know that sandy soil has higher or larger macropores, higher number of macropores or large sized pores is higher in case of sandy soil than that of clay soil. That is the reason, as the size of the pore space is more in case of sandy soil, hence the saturated hydraulic conductivity is more in case of sandy soil. So what is this hydraulic conductivity? That we will learn in this Darcy's law. Okay, so coming to next question, that is the choose the correct empirical formula or relationship that describes the Darcy's law. So now we'll study Darcy's law. So this is very important. So understand this Darcy's law. Then what is Darcy's law? Darcy's law says three important things. That is the flow rate. Darcy's law says that the flow rate is directly proportional to cross-sectional area A, and it is inversely proportional to the length of the pipe or length of the profile, and it is directly proportional to hydraulic head gradient. Hydraulic head gradient, or sorry, hydraulic head difference. So it is hydraulic head difference. So Darcy's law says that flow rate is directly proportional to cross-sectional area of the pipe. It is inversely proportional to length of the pipe, and it is directly proportional to the hydraulic head difference. Now we will see whether these things are correct or not. I will give some practical example. Okay, suppose we have two pipes. Suppose we have two pipes, and this pipe A and this is pipe B. Okay, so here the pipe A has higher cross-sectional area, and here the pipe B has lesser cross-sectional area. So here cross-sectional area is higher, and it is here the cross-sectional area is lower. So tell me, in which condition the flow rate, means water flowing per unit area, quantity of water or volume of water flowing per unit time, sorry, it is time. Okay, the unit of flow rate is centimeter cube per second. Okay, so volume per time, so quantity or volume of water flowing per unit time is the flow rate. So tell me, in which case, in A case or B case, in which case the flow rate will be higher? Definitely here the cross-sectional area means opening is larger, so here the flow rate means per unit time larger quantity or larger volume of water will be released. So here the flow rate is directly proportional to cross-sectional area. If cross-sectional area is higher, then flow rate is higher. So the first principle of Darcy's law is correct. So it is correct. Okay. Then coming to next principle, that is flow rate is inversely proportional to the length. So here two pipes are there. Suppose B pipe has lower length. It is a shorter pipe, but A pipe is a longer pipe. Okay, it is a longer pipe, but B pipe is a shorter pipe. So you tell me, in which case the flow rate will be higher? Because as A is a longer pipe, more resistance, internal resistance, because this pipe has some internal resistance. When the water will move through the pipe, it will face some internal resistance. So when water will cover a longer path for a longer period of time, definitely it will need longer resistance or higher resistance. But here the resistance will be lower in case of B. So definitely that is the reason why in case of length, shorter pipe has more flow rate as compared to the longer pipe. So that is flow rate is inversely proportional to the length. Then the second principle of Darcy's law is also correct with this practical example. Then coming to the third principle, that is flow rate is directly proportional to hydraulic head difference. Then what is this hydraulic head difference? Hydraulic head difference is the elevation of water as compared to a reference level. I'll just give one short example. Suppose three tanks are there. Okay, tank B is there, tank A is there, and tank C is there. Okay, for example, tank B, and this is the ground level. This is the ground level. So suppose tank B is kept at a height of 120 meter, and A is kept at a height of 50 meter, and C is kept as a height of 70 meter. Okay, then we will connect. If we connect this tank A and tank B, and tank B and tank C, so tell me, in which case the flow rate will be more? Higher quantity of water per unit time will be more in case of A. This is because the hydraulic head difference, because here it is 120 centimeter, 120 meter, and it is 50 meter. Okay, so here difference is 70 meter, but here it is 70 meter, it is 120 meter. So here difference is 50 meter. So here hydraulic head, that is del H, is 70 meter, but here hydraulic head difference is 50 meter. As it is more hydraulic hydraulic difference is there, and it is more steeper, water will flow at a higher rate in case of B to A than B to C. So the third principle of Darcy's law is also correct. So now we will combine all these things of all the principles of Darcy's law that says the flow rate Q Okay, flow rate Q, unit of flow rate is centimeter cube per second, is directly proportional to the area of cross-sectional area, that is unit is centimeter square. It is inversely proportional to length, that is unit is centimeter. Okay, and directly proportional to hydraulic head difference. The unit of hydraulic difference is also centimeter per meter, means length. Okay, so here we will combine these three things. When we will combine these things, always remember when we combine proportionality things into equation, there one proportionality constant comes. Okay, so here when we will combine these things, here Q and instead of this proportionality sign, when the equal sign comes, there one proportionality constant of proportionality will come. Okay, and this constant is K. So we will combine, that is A del H divided by L. I have just combined all these three principles of Darcy's law. So now the Darcy's law has become Q is equal to K A del H by L, where K is the hydraulic conductivity. Okay, K is the hydraulic conductivity. And what is the unit of hydraulic conductivity? Remember this thing. This is also important. In examination, it can be asked like, what is the unit of hydraulic conductivity? The unit is centimeter per second. Okay, so here the one thing we have derived, that Q is equal to K A del H by L. Okay, now we'll convert this thing into different things. Okay, so when this del H by L is known as hydraulic gradient. Okay, this del is known as hydraulic difference, head difference, and del H by L is the hydraulic gradient. So now this hydraulic gradient we can write I. Okay, so now the Darcy's law has become Q is equal to KAI. Okay, so the first option is correct. The second option is also correct. Q is equal to KAI, where I is the hydraulic gradient. And what is the unit of hydraulic gradient? It is unitless. Okay, because hydraulic head difference unit is centimeter, length unit is also centimeter, so it is unitless. Okay, I is unitless. Okay, then third thing. So here, when Q is equal to KAI, we can bring this A towards a Q. So here it will become Q by A is equal to KI. Okay, then what is this Q by A? Q by A is your velocity. Q by A is equal to velocity, and we can denote this V. So now the Darcy's law has become V is equal to KI. And what is the unit of V? It is also centimeter per second. That is the velocity. Okay, so option C is also correct. So what is the correct empirical relationship that describes the Darcy's law? The correct answer is all of this. Okay, so I hope it is clear to all of you. Here, remember one thing, Darcy's law, the original Darcy's law is always applicable to only saturated soil. Okay, original Darcy's law is applicable to saturated soil only, but with modification, the modified Darcy's law is applicable to both saturated and unsaturated soil. So with modification, we can use Darcy's law, means the principles of Darcy's law, to unsaturated soil also. So if question comes saturated, Darcy's law is applicable to both saturated and unsaturated soil, then the answer will be both saturated and unsaturated soil. Okay, then coming to the next question, that is Darcy's law is applicable when the flow is laminar or the flow is non-laminar, or the Reynolds number is more than 2000, or both B and C. So remember this thing, Darcy's law is applicable for laminar flow only. Laminar flow only means the flow is uniform. Okay, means when two layers of water, they are not cross section of, means there is no cross section of two layers of water, means water is flowing smoothly over one layer over other layer. Okay, that is the laminar flow. And laminar flow occurs when the Reynolds number is less than 2000. Okay, it is unitless, and when the Reynolds number is less than 2000, then laminar flow occurs. So Darcy's law is applicable when the flow is laminar. Okay, remember this thing. Then coming to next question, that is saturated hydraulic conductivity is higher in dark soil, sandy soil, loamy soil, or clay soil, or clay loam soil. We have already discussed that according to Poiseuille's law, saturated hydraulic conductivity is always higher in case of sandy soil. Okay, this is because saturated hydraulic conductivity is directly proportional to the fourth power of the radius. And we know that sandy soil has more number of macropores, means larger size pores. That is the reason sandy soil has more saturated hydraulic conductivity. But in case of unsaturated hydraulic conductivity, the hydraulic conductivity is more in case of clay soil, because unsaturated hydraulic conductivity depends on number of pore space. And we know that number of pore space is more in case of clay soil as compared to sandy soil. Then what if the question asks only hydraulic conductivity, means it has not mentioned whether it is saturated hydraulic conductivity or unsaturated hydraulic conductivity. So in that case, the correct answer will be sandy soil. Okay, the sandy soil has higher hydraulic conductivity than the clay soil. Then what is the reason? It has been found that the saturated hydraulic conductivity that occurs in sandy soil is 1000 times more than the capillary or unsaturated hydraulic conductivity. Unsaturated hydraulic conductivity is also known as capillary hydraulic conductivity. Okay, so it is simple. If question asks the saturated conductivity is higher in which soil, then answer will be sandy soil. And if it is unsaturated conductivity, then the answer will be clay soil. And if it asks what is the saturated, if it asks what is the hydraulic conductivity in which soil it is more, then the answer will be sandy soil. Okay. Then coming to the next question, that is when the point of consideration is below ground water table, the pressure potential, that is a component of total water potential, is positive, negative, zero, or pressure potential can be any value. Okay. So this question is from water potential concept. We have already discussed water potential, but in water potential has total water potential has three components. Okay, one is your gravitational potential, another one is your pressure or metric potential, another one is your osmotic potential. What is osmotic potential? That we have already discussed. What is total potential? That we have already discussed. Gravitational potential is due to the force of gravity. Now we'll discuss this pressure potential or metric potential. Okay, this pressure potential, it is the same thing. Pressure potential or metric potential is the same thing. Pressure potential is known as hydrostatic potential. Hydrostatic potential when the point of consideration is below groundwater table. So here the reference is groundwater table. Okay, if the point of reference means the point at which we are measuring pressure potential, if it is below ground table, then the pressure potential is known as hydrostatic potential and the sign of the potential is positive. Okay, and if the pressure potential or the point of consideration is above groundwater level, here below groundwater level means it is a saturated soil, means all pores are filled. So in case of saturated soil, or when the point of consideration is below groundwater level, then the pressure potential is known as hydrostatic potential and the sign of this potential is positive. And when the point of consideration is above groundwater table, and it means the soil is unsaturated, so in this case the pressure potential is known as metric potential and the sign of this potential is negative. Okay, so metric potential is always negative, hydrostatic potential is always positive. These are the types of pressure potential. Okay, now we'll see other signs of other potential. Gravitational potential is always positive and osmotic potential is always negative. We have already discussed that osmotic potential is negative in presence of salts and osmotic pressure or force is always positive. So now the pressure, now the potential concept in soil is clear. Okay, in next lecture we'll continue with potential concept in the plant cell. Okay, now the last question of the today's lecture. It is a simple question that 10 hectare millimeter is dash liter, means quantify 10 hectare millimeter water. Okay, suppose a farmer says that I have irrigated my 1 hectare land with 10 millimeter water, means land is there 10 hectare area and 1 millimeter means the depth of water applied is 1 millimeter. So it means that the water has covered 1 millimeter layer throughout the 1 hectare land area. Okay, now we'll quantify. Then it is very simple. That is 10 hectare millimeter. So here 1 hectare is 10,000 meter square and 1 millimeter. Okay, 1 millimeter is equal to 10 to the power minus 3 meter. So here we can write instead of 1 millimeter 10 to the power minus 3 meter. Okay, now it is 10 to the power 5, these two, that is meter square into 10 to the power minus 3 meter. Okay, so it comes 10 to the power 2 means 100. Okay, 100 meter cube. And what is 1 meter cube? 1 meter cube is 1000 liter. Okay, so here 1000 liter and it is 100. So here we can write 100 meter cube is equal to 100 into 1000 liter. So it is 10 to the power 5 liter. Okay, so 1 hectare millimeter, 10 hectare millimeter is 10 to the power 5 liter. Sorry, here option is not there, 10 to the 5 liter. Okay, so take this, 10 to the power 5 liter is the correct answer. Okay, so 10 hectare centimeter, it is nothing but 1 hectare centimeter. Okay, now the calculation is clear to you, you can easily calculate. So this is all about today's lecture. I hope now it is clear. In this way, we will cover the whole chapter of irrigation water management. And how was today's lecture? So give your feedback in the comment section. Thank you for listening. God bless you all.